This is a kinetics problem. Looking at this, we're asked about a half-life of a reaction. Looking up to the stem, we see that from the units, the reaction is first order, and in fact, we're told that it's first order. So we know for a first order reaction that T1/2 is equal to ln of 2 over k. We can put in our value for k. It's 1.8 times 10 minus 5 reciprocal seconds, which means seconds comes up on the top. If we calculate this out, we find we get 38,508 seconds, and converting that to hours, 3,600 seconds per hour, we get 10.697 hours, which with 2 sig figs is 11 hours. The molarity after 4 half-lives. This is a first order reaction, so we can take a shortcut. Since the half-life is constant. Let's directly apply the definition of a half-life. A of T is equal to our initial concentration times 1/2 raised to the n power, where this is the number of half-lives. So this is A naught is 0.30 molar, and we're going to multiply that by 1/2 raised to the 4th power, resulting in a molar concentration of 0.01875. And if we limit ourselves to 2 sig figs, it's 0.019 molar. Okay, the next question, how many hours will it take for the concentration to drop to 25% of the original value? We can take a shortcut. We know that this is going to be 2 half-lives. Again, we can exploit the fact that the half-life for a first order reaction is constant. So we can just multiply 2 times 10.697 hours. We'll go back to our original number to preserve sig figs, and our answer comes out to be 21.394 hours, and with 2 sig figs, that's 21 hours. Okay, alternatively, we can use the integrated rate law. ln of AT to A0 is equal to minus KT. Okay, 25% of its initial value means that A of T is equal to A0 over 4. So, if we want to write an expression for A of T over A0, we have A0 over 4 divided by A0, which just comes out to be 1/4. So, we go back to our integrated rate law, and now we can solve for T easily. T is going to be equal to ln of A of T divided by A0 divided by minus K. Make our substitution now. 1/4 is 0.25, and we have our value of K and we get our answer expressed in seconds as 77016 seconds. converting to hours, 3,600 seconds is equivalent to an hour, gets us to 21.393 hours. And it's no surprise that the two methods are in agreement, okay, within sig figs. Okay, the concentration of the reagent after 555 minutes. Now K is given in seconds, so let's kind of do that conversion. 555 minutes, every minute is 60 seconds. That leads to 3.33 times 10 to the 4th seconds. Alright, so we can plop this into the integrated first order rate law. ln of a of t to a0 is equal to minus kt. We'll expand this out using the properties of logs. ln of at minus ln a0 is equal to minus kt. So ln of at is equal to minus kt plus ln of a0. Okay, so this minus 5 seconds and times 3 times 10 to the 4th seconds plus ln of 0.30. Alright, this is equal to minus 1.803. And again, a reminder, that's ln of at. So a of t is going to be equal to e to the minus 1.803, which, if we calculate that out, is equal to 0.1647 molar, which with two sig figs is 0.16 molar concentration. Finally, the initial rate of the reaction. Here we have to go back to the original rate law. This is a first order reaction, which means that our rate is going to be equal to K times our initial concentration of H2O2. Again, we're talking about the initial rate. 1.8 is 10 to the minus 5, and it's multiplied by 0.30 molar, and our rate is 5.4 times 10 to the minus 6 molals per second, or we can express this as 5.4 times 10 to the minus 6 moles per liter per second.